Everyone. In today's video, we're going to be looking at overview of how the networking is set up within AWS. Specifically, if you're working with a customer-facing website, you're deploying it on EKS basically. So you're going to be receiving traffic from the user, from the internet, and then you forward the traffic into an application load balancer, and then from that load balancer you send the traffic across to your Kubernetes pods that are running. Now, the reason I'm making this video is because I have been having a discussion with a couple of junior DevOps engineers or platform engineers that are working with me and my mentees, who, after having a discussion with them, I realized that there is like a skill gap. Now, it's all good and great that you can, work with Kubernetes, set up your deployments, work with Helm, deploy things out there, you know how to roll back, about HP and all that is great. But network is a fundamental part also of Kubernetes, and it's really important to understand, especially if you're working in a cloud environment like AWS or GCP. And I think that's an important skill to kind of try and bridge across if you're trying to progress into a more senior role as a DevOps engineer or platform engineer, because it's really important. These are the decisions, these are the considerations or factors you need to take into consideration when you're trying to set up Kubernetes cluster, multi-cluster setup across multi-regions, and think about scalability, right? And this, even though I'm going to be talking about mainly focused around a customer-focused, customer-centric website that's open in the internet, it would also, a lot of these concepts and discussion is also going to apply to a Kubernetes cluster that's only serving internal customers, let's say, in a corporate intranet, right? So let's go ahead and get started. I'm going to sketch a diagram and sort of talk you through the different points to keep in mind across different, let's say, building block of this network that's set up, right, within AWS and EKS. So we're going to go ahead and first let's go and create like a kind of a container for our AWS. So this is our cloud, right? Our AWS, let's say it's our account that we log into in AWS. And now in this account, I've got a virtual private cloud. So let's go and pull this out, right? So I've got a virtual private cloud, or known as VPC, within AWS. Now, quickly, if you don't know what VPC is, think of VPC like a private data center. But only thing is that it's virtual and it's not physical. So private data center that's running in the cloud virtually, VPC just abstracts away all the networking configuration for it, right? So all of the resources that you want to run in your data center are networked and connected to each other through this virtual private cloud, right? They all live here. So this is your virtual private data center. And let's say we have this virtual private cloud in a specific region. So I'm going to go pull this out. So let's say this is in US 2. So let's say this is in London. This is in London. So I'm just going to go ahead and do EU West 2. Yep. Now, so you've got a virtual private cloud, and in the virtual private cloud, you've got a region. Now, even though this is with AWS, a majority of the concept would also apply to GCP and Azure as well. There are certain distinction, not so much from a traffic routing and definition point of view, but how things just work, how things are configured to work in AWS, GCP, and Azure differs slightly, but the principle is the same behind it all. So now we've got a region where we've got our virtual private cloud. Now in this region, let's go ahead and set up a public subnet, right? So let's go ahead and create a public subnet. We'll make this a bit smaller. And also, let's kind of say that this subnet is actually, before I do a subnet, let me create an availability zone, right? Because you would have your subnets across different availability zones within AWS. So let's go ahead and pull this out. So this is our availability zone here. And now we're going to go and drag our public subnet, which is going to be living within this within this availability zone. Yeah. And this availability zone is nothing but just within the same region. It's just a zone. So EUS2A, you may have seen this EUS2A, EUS2 references all over AWS. And let's say we are going to create 2 more of this, right? So, oops, let's say I want to copy this. So copy it here, and let's say we copy this down here. Let's say this is going to be US2B. Let's try this. There you go, much better now. So we go, let's space them out a bit. So let's move them out. That's it. And we've got EUS2C here. So public subnets, virtual private cloud, right? Now, what's a subnet? A subnet is nothing but just an isolated area within your virtual private data center, right? This VPC that shares a range of IP addresses, based on security reasons or routing reasons. You can have different subnets, or even from architecture point of view for high availability reasons, right? That's the setup here at least. So EKS in AWS recommends to have at least 2 to 3 different availability zones for highly available infrastructure, right? And it's a best practice to have so if you're serving load of traffic across the internet for a lot of your customer base. So now let's go and so now let's start off with a thing called CIDR, right? So let's say we're going to give our CIDR for the VPC is 10.0.0.0 and let's say we are at 24, okay? Which is an arbitrary number. Now you may ask, if you're not familiar with the CIDR, what exactly is this? Like what does this number or this notation mean, right? CIDR is basically a way to define or a range of IP addresses that belongs to a virtual private cloud. Now, every virtual private cloud, multiple virtual private clouds can share the same CIDR, right? That's no problem because it's private to you. It's your private data center. So there is no risk of like overlap. But if you're trying to connect 2 different virtual private clouds together and they both have the same CIDR, like if you're trying to peer them together, that's not going to work. In order for 2 virtual private clouds to be joined together, you need to have separate CIDRs. But if it's just your own area, own cloud, right, your own account, and you're setting up your virtual data center there, that's all good. Choose whatever CIDRs are more appropriate for you. Now, I say whatever, but that CIDR number is actually important. I'll come to that in a bit later in the video. But so this is basically. I'm not going to go into detail on what these actual numbers mean in here, right? What this 10.0, 10.0.0.0/24, right? How, like, what's the meaning behind each of them? All of that, I'll actually link to a different video because that's where I learned it from, and it's from Mr. Adrian Cantrill, who has got a good series of network-related videos, especially from a cloud point of view. And I'll link this video within my video so that you can, go in and dig. If you wanted to dig deeper and understand it a bit more, then feel free to go there. But for the purpose of this video, I'm not going to go in depth on that. That's something I think needs a session of its own, to be honest. So if you wanted to understand that a bit more, then I would recommend you to go visit that link that I'm going to be attaching to this video. But I'm going to show you the tools that we can use to sort of understand how can we now distribute a CIDR that's been given to a virtual private cloud to these subnets, right? Like what does this really mean? So let's go ahead and get like a CIDR calculator, right? Now, CIDR to IPv4 address range utility tool, and there are quite a few different versions of them all over the internet, right? You can just choose whichever you want. I usually go to this one because it's pretty good. It gives me the first and the last address within this range and a few other information, which is usually useful, right? So let's go ahead and put this in here and let's calculate. So what this is telling me that there are 256 IP addresses available within this CIDR, right? So within this virtual private cloud, I've got 256 IP addresses, where the first IP is 10.0.0.0 and the last IP is 10.0.0.255, right? Now, obviously that's across my whole virtual data center. How do I now distribute it out to the subnets? And if I do so, how does the actual range look like, right? So subnets are also going to have their own CIDR, so IP address range. And every subnet should have their own CIDR range, right? In the virtual private cloud, you cannot have the two subnets sharing the same CIDR, right? They shouldn't be overlapping either. You should have clear distinction between them. And this applies to both public and private. I'll come to private subnet in a bit, but let's talk about public subnet, right? So the reason public subnet means whatever workloads you run, they're going to be you should be able to access them over the public internet, right? It's going to have, so let's say you're running an EC2 instance in a public subnet. It's going to have a public IP address. So you could, if you wanted to SSH into it, you could use this public IP address and SSH into it. If you wanted to forward traffic into it, it would be much more easier to forward traffic to it, right? If you just expose it out to the internet, you could hit it directly based on the IP address and the port of that virtual machine. Now, obviously, it comes with a security risk, right? There's massive amount of attack surface then if you're running your workloads in the public subnet. And that's where private subnets sort of come in and step in, right? So in a typical EKS workflow where you're serving multiple customer base over the internet, you typically have your public subnet still. And in the public subnet, you would have an application load balancer, let's say, right? Or some sort of load balancer. It doesn't have to be application specific. It doesn't have to be like an AWS specific load balancer, right? You could use Nginx load balancer too, for example. And applies to GKE, Azure, the same concept. So you have your load balancer in the public subnet, and that would have an IP address, which is what your customers would be hitting, and that load balancer would then be configured via an EKS ingress resource to forward traffic to the actual pods that you're running in the virtual machines within your EKS cluster, right? I'll come to that in a bit more depth a bit later, but I just wanted to sort of explain the reason for public subnet. And private subnet, now private subnet is where majority of the workloads are run in your Kubernetes, all your data processing, all sort of processing based on like an incoming HTTP request. All that should happen in a private subnet, right? Because it reduces the attack surface massively because these are not exposed over the internet. You can't just hit an IP address and with a port and hit it from your terminal, right, to SSH into it. You can't do that because they are not exposed over the internet. And also the private subnets still need a CIDR as well. So it's basically an IP address range similar to public subnet. Your private subnet should have it too. And again, public subnet, private subnet, they're still subnets, so they shouldn't be sharing the same CIDR or overlapping, right? So now the next question is, how do we take a CIDR of VPC and then distribute it out to each of the subnets, right? So let's go ahead and actually add some private subnet here as well. So let's go ahead and add private subnet. So AWS's recommendation is that EKS within AWS as a recommendation that if you are running workloads, then you should have at least 2 to 3 pairing, 2 to 3 private public subnets separated by their availability zones within your virtual private cloud, right? This is mainly to give a highly available architecture for if you're running microservices to scale in Kubernetes using EKS. And lastly, we're going to move this one down in here, right? So you got public subnet and a private subnet in each of our availability zones within our virtual private cloud. Now let's start simply. So we're going to take this CIDR, so these 256 addresses that we've got, and we're going to distribute it evenly across each of these subnet. I'll show you how to do that. So we've got our first IP address, right? Which is this 10.0.0. So since we've got 256, we're going to just go and let's get an online calculator out. So let's say we've got 256 and we divided that by, let's say 6. So let's say about 42 addresses, right? Let's split it like that. So we give 42 addresses to each of our subnets. Now we basically then need to calculate the CIDR that will give 42 hosts at least. So which would be, let's try 26. So you got 64 there. So we're not going to get 42 exactly, but we need to go to the closest one, I'll say. Right, so let's go with 32. So let's do this as our CIDR, right? We're going to go. So in this CIDR range, let me just write this down. So let's say the CIDR here is this, okay? So what we're saying here, that in this public subnet, the first host IP address, the first IP address is 10.0.0.0, and the last one is 10.0.0.31, right? Now the next subnet should start with 10.0.0.32, right? So I'm going to do 10.0.0.32/27. So that will give me another 32 host, with the first IP being this. So we're just going to copy this as the CIDR range, come down in here, and let's say this is our CIDR, right? Oops. There you go. And then lastly, we're going to go and look at the last IP address. So we are now going to be at 64. So CIDR here is going to be 10.0.0.64/27, which would then basically give us another 32 IP addresses, right? So the next one being 10.0.0.95. But is that what we want to do though, right? Do you want an even distribution of these CIDRs across all these different subnets? Answer is no, we do not want to do that. Because in your public subnet, you don't really want to have that many. Whereas in your public subnet, you do, because that's where all the workloads are going to be running, right? So what you would really do is, it is always going to be an uneven distribution where private subnets are going to have majority of your IP addresses. So their range, their CIDR range is always going to be much higher than the public. So we're going to actually go ahead and assign them to this private subnet instead. So each of these private subnets have, let's say 32 hosts for now, even though there is much more capacity than VPC, right? And in the public subnet, let's say I actually want to just do 8 hosts, right? 8 IP addresses. So for that, I'm just going to go and do, let's say 30. So 30 is going to give me 4. So let's just do 29 then. It's 29. And you can see the way this either the hosts are going to change based on how you increment the range number, which is the number after the slash. It always doubles. So if I do 28, there will be 16 hosts, and if I do 27, there will be 32 hosts, as you saw, and so on. Every time it will double, basically, depending on how you increment or decrement it. So we're going to use this to our public subnet, right? And again, AWS Contrails playlist on the networking fundamental has even more deeper concepts about how the CIDR addresses are actually allocated. Not all of these IP addresses are actually usable, are there to be used by resources within your network. Some needs to be automatically used when you're running it in the cloud, right? And some don't. And some are going to be used for your actual resource. And then lastly, we're going to go ahead and change this to 29.2. So you've got 32 hosts in the private subnet, and we have 8 hosts in each of the public subnets, right? Cool. Now, with this information, let's go ahead and look at what actually is going to happen then to an EKS, right? Specifically at a worker node. And we'll come back and look at the public subnet a bit later. So let's go ahead and kind of bring another block of Amazon Cloud. Only thing now is that we're going to be, zoom out a bit, make it bigger. Instead of Amazon Cloud, I'm just now going to replace this as EKS. And within the EKS, I'm going to now, let's say, create EC2s, right? So let's go to compute here. Compute, and let's find EC2. Okay, let's get an EC2, right? Let's think this is an EC2 instance. And we've got another one here, and we've got another one here. So 3 EC2 instance, and we're kind of zooming in now. I'll just highlight on this particular private subnet, right? Let's say all of them are attached. Actually, I'm going to move them down a bit. So all of these 3 EC2 instances are actually attached to, let's say, this one private subnet, right? Although it's going to be happening across all the different private subnets, all of them are going to be attached to a group of EC2s if all are to be used by the EKS cluster, right? But I'm just going to, for explanation purposes, I'm just going to be focusing at one subnet, and let's say each subnet, or let's say one of these subnets have got 3 EC2 instances. Now, how does the EC2 instance get linked to a private subnet, right? It gets linked through the usage of a thing called elastic network interface. So let's bring up the icon for that, which is somewhere around here, I believe. Yeah. So in short form, they're known as ENI. Now, what is an ENI and why are they important? Which is a fundamental concept that every platform engineer and DevOps engineer should know. So an ENI does a bunch of things, right? Think of, first of all, what is it? So elastic network interface is nothing but a virtual network card that's attached to your EC2 instance, right? So, and because of this, your EC2 gets a link. So this is how your EC2 gets linked to a subnet, to, let's say, security groups. It gets a MAC address because of this. And also because of this, it gets a private IP from the virtual private cloud or from whatever subnet it's linked to. And optionally, it can also get a public IP if it's on a public subnet, right? But all of that is possible because of elastic network interface. So whenever EC2 instance on EKS, so every EKS cluster worker node is going to be attached to a subnet. And that subnet is going to provide that node or the EC2 instance with IP address, private IP address, definitely, right? And that's how it's then connected to your data center, essentially, the virtual private cloud that we spoke about at the beginning of the video. So let's go and kind of write up a sticker just to kind of highlight what this really mean. Yeah, and let's actually move them a bit so we make some space for ourselves here. So let's grab them, move them here. Let's get this a bit more bigger, and I'm just going to list out all the different things that EC2 gives us, right? So a private IP, we get it. Then we get a public IP. If in public subnet, then we get a link to subnet itself. Let's make the font a bit more smaller. That's too small. Let's do 12. And then it also allows, and ENI also allows link to security group. And then it also gives the EC2 instance a MAC address, right? That's what ENI does. And now ENIs are something that you don't need to go and set up. It's automatically sort of provisioned and set up for you by AWS. And these are essentially known as your primary ENIs, yeah. However, there is another important aspect, especially on the EKS world, which is called the secondary elastic network interface, or secondary ENIs. And they're also very important, right? So let's go ahead and kind of copy this. So let's say we've got this EC2 instance, and in this EC2 instance, we've got multiple pods running, right? So let's go ahead and get some container. Compute. So let's say we get a container, right? So let's say we got 3 of them here, yeah. And each, let's make this a bit more bigger, and let's say each of them has an IP address. Let's say 10.0.0. What subnet are they? So let's say they're all coming from, let me put an arrow in just so that it's all very clear. So all those will get connected over here, yeah. And actually, let me centralize this thing a bit more so that it's more easier to follow. Yeah. So so essentially we're taking kind of a bird's eye view within this private subnet, and the nodes that are connected, the EKS worker nodes that are connected to this private subnet, right? And now we're kind of taking a bird's eye view of the containers that are within one of these worker nodes. And it's the same story that's going to happen across the different nodes as well. And as I illustrated before or highlighted before, same thing is going to happen inside every other private subnet too, if they all are used for the EKS worker nodes. So let's go down to here. Let's go down here. And let's go down here, right? So all of them, and this one, we're going to call it as a secondary elastic network interface, right? So this text, and let's make it okay, let's leave it a bit to the, yeah, let's just leave it to the left. Just wanted to make it a bit more easy to read, but looks like there are issues happening at the moment. But yeah, secondary elastic network interface. Now, what this does, so first of all, these are again something that you don't have to go and typically manage if you're provisioning your EKS cluster, let's say through Terraform, or even setting it up manually. These automatically gets provision and setup for you through a plugin called VPC CNI. So VPC CNI plugin essentially, if you wanted to go into depth about it, I'm going to attach a link in this video or to an article that describes it very well. But essentially, AWS adds this plugin called VPC CNI in the EKS cluster, which essentially allows the pods that are running within a particular worker node to essentially borrow and use IP addresses from the subnet that the worker node is connected to. So in this case, the pods are also going to get real IP addresses from your virtual private cloud, essentially. And they're going to be specifically coming from the subnet where the worker node itself is connected to, right? Any addresses that are free to use. So in our case, let's say this is going to be 10.0.0. And let's say we were at the beginning, right? So, I actually should have done this more better. So this should have been 31 here, and we should have had it from 32, and here we should have had it from 64, right? So we're going to get, let's say, arbitrary address, right? It's going to be ephemeral here. So 10.0.0 dot, let's say, 23. And then in here, this pod may get an IP address of 10.0.0 24. This one may get an address of 10.0.0.25, right? All of this is going to come from the subnet. So in this particular example, we're looking at this subnet, which is a IP address range of 10.0.0.31/27, right? So the last IP address here is 10.0.0.31. So we're just getting something before the last IP address. But essentially, this IP address allocation is all done under the hood and managed through VPC CNI. However, you can see that it's actually using real IP addresses from your subnet. Now, this is why it's important to understand how it works and that secondary ENIs exist and how they work, right? Because let's say you don't have any more IP address left in your subnet, you've got all allocated to the nodes. So how are the pods now actually going to go and use these IP addresses, right? Because in order for the pods to actually communicate between each other and also through, let's say, your control plane, or if you're trying to reach it through a load balancer service, right? It still needs an IP address. Now, if there is no more IP address left in the subnet, then there's IP address exhaustion. And this is why when you are designing a large-scale Kubernetes cluster, it's important to keep in mind and start with how much you really want this cluster to expand and scale, right? If you see the need of multiple pods to be running, right, then you need to kind of take that into consideration too, on how many CIDRs that you should really set your VPC to. So this one that we're talking about in here, right? In my previous experience, we have had to, since these workloads, I've been working in this industry for about 9 years now. And when I initially started, a lot of these kind of conversations were kind of new, right? Running a large number of workloads that are scaling rapidly was just starting to evolve at that time. And a lot of existing virtual private clouds and infrastructure were not really suitable for it. So we needed to kind of design our clusters to be think for the future and kind of be expandable, and so that our pods and our workloads can grow into it, or the cluster can grow into it, and you can have multiple of these clusters, right? If you're thinking dev environment, prod environment, staging environment, maybe you need a virtual private cloud set up for each of them individually, right? Depends on how your setup is. Most of the time, I guess they are separate as a best practice, because then all of your dev workload, production workload, staging workload are isolated from each other. So your security point of view, that's great. scalability point of view, availability point of view, they also don't interrupt with each other, and you get your isolated environments to do your tests in before promoting anything to prod. So all those benefits are there. However, if you do want to, for ease of managing things and provisioning infrastructure, right, and deployment, you can choose to keep all of them in the same, let's say, project, right? You could have 3 different clusters attached to the same virtual private cloud too. So in those cases, it's even more important to plan well ahead with what your CIDR range should be for your virtual private cloud, right? For your virtual private data center. Because trying to kind of go back and re-engineering these things is a bit more expensive and time consuming, and yeah, not the most efficient really. And without understanding how secondary ENIs work, this kind of discussion or factors doesn't really come into mind. And I just wanted to highlight this, and that's why I kind of went through from the very beginning and the scratch of how you should go about thinking when you're trying to set up these infrastructures. Also notice this is incorrect. This shouldn't be 64 in here. This could be, let's say, something like 65 to 29, and this say could be 64 27. Let me just do it. So the last IP address here is 10.95. So 10.96. And then we've got 10.96. I always come back to this tool to kind of help me look at how many IP addresses there are. What's the last one especially? So here we have got 103. Also, to be fair, it's just 8 hosts. And here we're going to have 111. So you can have up to 255. But again, that's best to watch Adrian Cantrell's video on it, which I'll link here. So that will give you much more better understanding of how this works. I could talk on it, but that will just make this session more and will make it even more confusing. So I'm purposefully and intentionally skipping over it. But yeah, but that's how your typical allocation could look like, right? For a CIDR of this. And you can see that I've left quite a lot of room here so that my pods, because of the secondary ENIs, can come in and leverage those or use those free IP addresses. Another way you could sort of take into or tackle not exhausting these IP addresses is trying to fit multiple pods per secondary network interface, right? So in this example, I'm just showing one for ease of understanding and explanation. But in reality, depending on your instance type, in your EC2 instance type, you could have multiple secondary elastic network interfaces for just one worker node. So the more network interfaces you've got attached to a particular node, the more pods you're going to have. So if you're choosing like different types of machines that can support multiple secondary elastic network interfaces, means you can fit more pods into it. So less usage of IP addresses. So you could use IP addresses more efficiently that way as well from your virtual private cloud. But the most easiest and probably the most recommended way to do is by having a decent size or well-planned CIDR range for your virtual data center itself. And yeah, now in a future video, I'm going to be going through internet gateway, NAT gateway, and the load balancer and how it kind of sends traffic across the subnets all the way to the pod and how the pod communicates back with the external world or the internet, right? Let's say if the pod wanted to go and fetch some packages, Python packages or some dependencies, or a user is trying to reach or trying to use your front-end browser to do something, right? There's an A request. How does that get propagated within the AWS VPC all the way to the EKS? So stay tuned for that future video.